We're now prepared to apply the transformation theorem, and we'll start off looking at some rotations. And rotations, we're just going to state here, they are linear transformations. They do follow the two properties of indifference to scaling and indifference to addition. So that means we can, if we know it's a linear transformation, we can construct the A matrix. So we want to rotate a vector in 2 dimensions by 90 degrees, which is pi over 2 radians, in the counterclockwise direction. Find the matrix that performs this operation. Okay, so we're going to start off with stating our transformation. So it's going to take a vector in R2, and it's going to output another vector that will also be in R2. It's going to rotate it by 90 degrees. So that means that n is equal to 2 and m is equal to 2. And we expect A to be an m by n matrix, which should be a 2 by 2. All right, so first thing we need to do is list out our vectors in the starting dimension. E1 is the vector 1, 0, and E2 is the vector 0, 1. So what we need to do is we need to transform each one of those. So we need to transform E1. Okay, so in other words, what we need to do here, this is where we'll get the specific values. E1 is the vector 1, 0. 1, 0. Okay, and sometimes it makes sense to do it visually. Sometimes you don't need to do it visually, but it might be helpful to visualize what that transformation will actually look like. Okay, so now rotations take place either clockwise or counterclockwise. In this case, we're going counterclockwise, and that means that our transformation will rotate this thing 90 degrees. And it's not going to change its length, right? It's still exactly the same length because all we're doing is rotating it. Well, you can probably already visually see that now it's pointing straight up, and that's the vector 0, 1. So, in conclusion, what we're going to be able to write is that the transformation of the 1, 0 vector is the vector 0, 1. We do the same thing to E2. Now, maybe you can already see what a 90-degree rotation will look like, but a 90-degree rotation for the 0, 1 vector, remember, this has to be counterclockwise. That's going to be 90 degrees this way, and that will just produce a vector that points directly to the left, same length, and that vector would be labeled as negative 1 unit to the left, 0 units up or down. And so the result of rotating the 0, 1 vector counterclockwise by 1 unit is the vector negative 1, 0. Now the transformations theorem says that you can take the transformation of E1 as your first column and the transformation of E2 as your second column. And so the transformation of E1 is 0, 1. The transformation of negative 1, 0, of 0, 1 is negative 1, 0. And that is our A matrix. So what we should be able to do now is if you take a, let's say we'll kind of pick a vector that, let's say 1, 1, okay? If we took the vector 1, 1, and we rotated it 90 degrees, it should, counterclockwise, it should point like that, right? It should be a 90-degree angle there. Let's see what we get as an output. 0, negative 1, 1, 0. So this is our transformation matrix. And now we want to transform the 1, 1 vector. So we did it with the basis vectors, and hopefully that implies that we could do this to any vector now. So take our matrix, multiply it by 1, 1. So 1 times this guy plus 1 times this guy would give us the vector negative 1, positive 1. And check it out, that is exactly what we should expect to get. The vector that basically, if this is 45 degrees, this is 45 degrees. It should split that second quadrant in half, if you will, and make it into the vector negative 1, 1. So to build our matrix, we just have to transform the 2 basis vectors, and then once we have that, we take those 2 transformed vectors and form the columns of the A matrix. As long as it's a linear transformation, it's going to work. So in the next example, let's take a look at a rotation by theta radians. So we'll actually work with a simple case here. Let's say we work with 45 degrees, which would be theta equals pi over 4 radians. Thing as saying 45 degrees. I'm going to write 45 degrees, but we know that we want to be able to do radians here. So the first is realize that, again, our transformation takes a vector in R2 and produces another vector in R2. So n is equal to 2, m is equal to 2. In our starting dimension, we have two basis vectors, basically same setup as example 1. This is going to be another one of those cases where I want to draw it out, because in order to figure out what is the transformation of E1, I need to visualize, well, what would a 45-degree rotation do? And these vectors are going to be 1, 1, and negative 1, 1, but the point here is to generalize this to any theta, so we'll see how we do that in just a moment. So let's start off by drawing the vector 1, 0 and imagining what would happen if we rotated that counterclockwise 45 degrees. So it would look like this. Now notice it's the same length of 1, but it wouldn't quite reach to the tip of where it was because it got rotated. So we form a new vector here, which to figure out what x and y are of this new vector, we make a right triangle. And what we know about this is it has a hypotenuse of 1 and an internal angle of 45 degrees. This is x, this is y. And since it's a right triangle, we can form sine and cosine of 45 degrees. We don't want to do tangent because it'll do y over x, opposite over adjacent. And we don't want two unknowns in a trig expression, a trig equation. So if we do sine of 45 degrees, well, that'll give us y over 1. If we do cosine of 45 degrees, that'll give us x over 1. And this is the beauty of working with unit vectors. We already know that without having to isolate y, that y is sine of 45 degrees. X is cosine of 45 degrees. And those are the components that we're trying to resolve. Those components represent the transformation of E1. And so E1 will be the vector cosine 45 degrees and sine of 45 degrees. Now to do E2, we're going to draw the same thing, except that's going to be the vector 0, 1. And if we rotate that guy 45 degrees, 45 degrees will look roughly like that. And now we can form a right triangle, but I'm going to form it relative to the vertical axis. I don't want to do it down here because if this were, say, a 60-degree rotation instead of a 45-degree, then this would be 30 degrees. What happens is because I picked 45, that both the interior and exterior angles are 45 degrees. But we don't want to change the angle. We don't have to reference a different angle. So we're just going to reference the rotation angle, the 45 degrees. Now in this triangle, notice that this is the y and this is the x. And we know that x is going to be negative. So actually I'm going to, for a moment, rather than call them x and y, I'm going to refer to them as a and b. I'm going to refer to this as a and this as b. And the reason I'm going to do that is because I'm not going to worry about SIGN signs. I'm just going to focus on resolving that triangle. So let me actually just draw the triangle this way. So it's as if we're just looking at this being b. That's this side right here where that 90-degree angle is. This is a, and this is our hypotenuse of 1. So to solve for b, I could take sine of 45 degrees, and that's going to give me b over 1, which is just b. Cosine of 45 degrees will give me a over 1, which is just a. And now let me think about what x and y are here. Well, x is going to be the negative of whatever b is because it's in the second quadrant, and x's are negative over here. And y is going to be a because it's going to be a positive number since it is above the x-axis. So if x is negative b, b is sine of 45 degrees, it's going to be negative sine 45 degrees, and a will be a over 1, which is cosine of 45 degrees. And there we go. So now x is negative sine 45 degrees. X is cosine of 45 degrees. And recall that our A matrix will contain the transformation of E1 as the first column, transformation of E2 as the second column. And what are those transformations? They are cosine 45 degrees, sine 45 degrees, negative sine 45 degrees, and cosine 45 degrees. And this matrix, if you multiply any vector by that matrix, you will get a vector that is rotated 45 degrees counterclockwise. Pretty cool, right? Now, if you just replace these angles with theta, then they will perform any angular rotation that you want. So if you replace theta with pi 6, that would give you a 30-degree rotation. And yet, all you would have to do is change the 45 degrees to 30 degrees, and it would perform that transformation for you.